When we use the Laplace method to solve differential equations, often we find ourselves using partial fractions. Often we find ourselves completing the square. And often we find ourselves doing both. And I don't think we've done any examples using both, so let me do that in this video. So we know that if we have a fraction, a rational function, so that's polynomial over polynomial, like let's say the top one is p of x, and let's say the bottom one factors as x squared plus 1 times x minus 4 squared times x plus 3 with the degree of the numerator less than the degree of the denominator. Here the degree of the denominator is 2 plus 2 plus 1. So that's 5 here. Then we can write this as a over x squared plus 1. Sorry, ax plus b over x squared plus 1, because this is irreducible of degree 2. So we need an x term and a constant term. Plus c over x minus 4 plus d over x minus 4 squared. Now since x minus 4 appears with the second power, we need to have a denominator for its first power and second power. If this were cubed, we would need first power, second power, and third power. And then finally, e over x plus 3. Then we can multiply both sides by x squared plus 1, x minus 4 squared, x plus 3 to clear denominators. Then we can plug in x equals 4, x equals minus 3 to solve for some constants. A, B, C, D, E. Then maybe plug in x equals 0 to solve for more. And then finally, when we get as much as we can get by plugging in different values of x, then we can compare coefficients of 1, x, x squared, x cubed, x to the 4th on both sides. To solve for the remaining constants. So that much is probably all review. The trick I want to point out is that sometimes there's an irreducible polynomial of degree 2 that's not as obvious as x squared plus 1 or x squared plus 4 or x squared plus 9. Sometimes it looks different. And we really apply the same procedure. We just have to be ready for denominators that look like that. So the procedure is really the same if the denominator contains an irreducible polynomial of degree 2, which is more complicated than x squared plus 1. Maybe it'll be something like x minus a squared plus b. So it gets its own fraction with ax plus b on top, just like x squared plus 1 did. So let's do an example. So let's say we're taking the inverse Laplace transform of a function. Let me call it just capital F of s for now. And then I'll write capital F of s is, let's say it turns out to be s squared plus 7s minus 28 over s squared minus 6s plus 25 times s minus 1. And let's suppose that this factorization of the denominator is given to us on a silver platter. It might not be in real life, but if it is, great, then we have less factorization to do. So as it is, it doesn't look like something that we have memorized. So we have to massage it, turn it into fractions that we're going to recognize, and then we can take the inverse Laplace transform of those. So we can write this as as plus b over s squared minus 6s plus 25. And by the way, if we take negative b plus or minus square root of b squared minus 4ac, just to see if we can factor this, I guess we have negative b plus or minus square root of b squared minus 4ac all over 2a. So we can see what's in the square root is negative, so we're not going to have any hope of factoring this over the real numbers. Alright, so we can write this as as plus b over s squared minus 2s plus 25 plus c over s minus 1. Then let's clear denominators. So on the left-hand side, we'll have s squared plus 7s minus 28 equals, on the right-hand side, when we multiply by this, the first factor is going to cancel the denominator, and we'll get as plus b times s minus 1. And then s minus 1 will cancel this s minus 1, and we'll get c times s squared minus 6s plus 25. And maybe it'd be convenient to write this as s minus 1 plus b s minus 1 plus c times s squared minus 6s plus 25. Alright, so this suggests plugging in s equals 1, because if we do, then the first and second terms here will disappear, and we'll just solve for c pretty easily. So if we try plugging in s equals 1, on the left-hand side we have 1 plus 7 minus 28, which I guess is minus 20, equals, that disappears, c times 1 minus 6 plus 25. That's 26 minus 6, that's 20. So if negative 20 equals c times 20, then that means that c equals negative 1. Alright, so then we can try plugging in s equals 0. And I guess we know that c is minus 1, so we can just write that. So try plugging in s equals 0. So that'll make this part go away, and then we'll solve for b. So on the left-hand side we have minus 28. This term goes away. We have b times minus 1. C we know is minus 1. And next to C we had 0 minus 0 plus 25. So minus 28 equals minus b minus 25. If we add 25 to both sides, that says that minus 3 equals minus b. So I guess b equals 3. So we've solved for c and b. Now we need to solve for a. Now I don't think there's any other good numbers to plug in. So let's compare coefficients of s squared on both sides. So on the left-hand side we have 1s squared. Then we have as squared here. No s squareds, plus cs squared. C is minus 1. So I guess that means that a equals 2. So we want to find L inverse of a is 2. So 2s plus b is 3. 2s plus 3 over s squared minus 6s plus 25 plus c over s minus 1 plus minus 1 over s minus 1. Alright, this fraction is going to be easy. That's going to be an exponential. This one we need to massage a little bit more, because it doesn't quite look like anything we know. This looks a little like something over s squared, or maybe something over s squared plus something squared, or maybe s over s squared plus something squared, or a combination of these. And if we can express it as a combination of these, then each one of those individually is easy to take the inverse Laplace transform of. So let's start massaging. Now the bottom looks a little bit like, if we were to complete the square here, this looks like s minus 3 squared. S squared minus 3s gives us minus 6s, plus minus 3 squared is plus 9. So that looks, these start the same way. So let's write this, let's take 9 out of the 25 and then put 16 aside. So 2s plus 3 over s squared minus 6s plus 25 equals 2s plus 3 over s squared minus 6s plus 9 plus 16. So we're just writing 25 as 9 plus 16. And then that is 2s plus 3 over s minus 3 squared plus 16. Alright, so that looks like we're going to get the sine and cosine here, because in the bottom we've got something squared plus a perfect square. The trouble is in the numerator we really want s minus 3 or 4. We want to have one of these forms. So we don't exactly have that, but we can massage it and get a multiple of that or a sum of things like that. So I really wish I had s minus 3. I have 2s. If I write 2s minus 6, that'll be 2 times s minus 3. 2s minus 6. Of course, I'm going to add in 6 if I subtract 6 so that I'm not lying. I don't want to change the expression. S minus 3 squared plus 16. So now this is 2 times s minus 3 over s minus 3 squared plus 16 plus 9 over s minus 3 squared plus 16. Alright, now the first fraction is pretty good. You can just pull out a 2 and it's exactly the form we want. The second one, I kind of wish I had a 4 instead of a 9. So we can massage that a little bit more to make that come true. So we have 2 times s minus 3 over s minus 3 squared plus 16 plus, I can pull out a 9, and then I really wish I had a 4 here, so I'll just multiply by 1/4 on the outside. Multiplying by 4 over 4 doesn't change anything. S minus 3 squared plus 16. Now I don't want to lose this minus 1 over s minus 1. So far we've been playing with the first part. Maybe I'll just write it now. So this fraction we wrote as that. So we have 2 L inverse of s minus 3 over s minus 3 squared plus 16 plus 9/4 L inverse 4 over s minus 3 squared plus 16 plus L inverse of minus 1 over s minus 1. And actually, why don't I pull this minus 1 out and say minus L inverse of 1 over s minus 1, because then that fraction's sort of ready to go. Alright, now since L inverse of s over s squared plus 16 equals cosine of 4t, and L inverse of 4 over s squared plus 16 equals sine of 4t, then these shifted versions with the s minus 3 are just the same things where we multiply by e to the 3t. So we have 2 e to the 3t for the shifting cosine of 4t plus 9/4 e to the 3t for the shifting sine of 4t minus just e to the t is the inverse Laplace transform of 1 over s minus 1. And that matches my notes. And that's it. The end.